Okay, so I will make a very brief introduction of Mithat Unsal. In fact, in this audience, it's probably not necessary at all, because basically the very existence of this program at the Isaac Newton Institute was due to, in a sense, due to the ideas which were planted in physics community through the efforts of Mithat Unsal and his collaborators. But here is a little bit of his data. He was born in Turkey and got his undergraduate education in Turkey. Then for the graduate education, he moved to Washington University, where he defended his PhD in 2004 under the supervision of David Kaplan. His interests are almost entirely focused on quantum field theory, and in particular Young-Mills theories in non-perturbative regime, which is sort of a perennial subject, despite the fact that QCD exists, or Young-Mills theories exist already for half a century. This progress in this particular area, non-perturbative effects, is not by any means complete. So here I only briefly mention two major advances due to Mithat and his collaborators. One is the notion of adiabatic continuity in gauge theories, and including the discovery of a huge class of new quasi-classical solutions, which exists only if you compactify one of the spatial dimensions instead of considering Young-Mills theory on R4. This is a flourishing area with many people doing research there using this idea. And the second is basically the subject of this program, is the resurgence applied to physics. In mathematics, it was discovered, I mean, the whole idea was put forward by Jean Ecaille. If I pronounce his name correctly, I'm sorry, it's a French name, and I have never met Professor Ecaille, so I never heard the correct pronunciation, but you can correct me. And it was known and used in some mathematical circles, but not too widely. And Mithat pioneered in understanding this whole idea in physical terms and transplanting it in the ground of theoretical and mathematical physics. And in many instances, it works perfectly, like for instance, in quantum mechanics, in partial differential equation, in many, even in some field theories where the coupling constant doesn't run too much. But in the field theories where it runs, like pure Young-Mills field theory, it's still in the process of development. But the whole, I mean, set of talks, I didn't attend all the talks, but most of them I have attended at this program. They speak for themselves, so to say. So with this brief introduction, I will let Mithat to present his today's talk.
Okay, thank you very much, Misha, for very nice introduction. I think the only way I can go from this critical point is downhill. So I hope it will not be very disappointing, my talk. So the title of my talk is actually partly borrowed from a talk that Michael Berry gave a long time ago, Stokes and the Rainbow. So my title is From Rainbow to Mass Gap and Resurgence and Lefschetz Thimbles at Work. Okay. Let me first tell you a motivation, then I will describe what is going on more generally in quantum field theory. Now, all of us know the concept of mass in classical mechanics, and we first encounter with the concept of mass through Newton's second law, where it tells us that force is equal to mass times acceleration. Here in classical mechanics, mass is an intrinsic property that we associate with bodies. So it is given quantity. However, in some quantum field theories, mass is an emergent concept. By this, what I mean is that a microscopic quantum field theory with no mass parameter in its Lagrangian may very well induce a mass. This is actually what's taking place roughly in nature. The part of the standard model that generates almost all mass of the visible matter in the universe is called quantum chromodynamics, QCD. So there is a quarkless version of QCD, and it is Yang-Mills theory. And this thing is generalization of the Maxwell's electromagnetism. And instead of electric field, say in X direction, you replace it by traceless 3x3 matrices. In Maxwell theory, we all know that the propagation of wave occurs in vacuum at the speed of light and can possess any positive frequency. That means there is no mass gap. So this is the reason that we teach about these linear waves in the high school or other grade, school level. However, Yang-Mills equations are nonlinear. They have nonlinear solutions which also classically travel at the speed of light, but we never observe these waves. So with the electromagnetic waves, the reason you are seeing this page is because of the interaction of our eyes and brains with these waves. So we never observe Yang-Mills waves. The reason for this is something called mass gap, a quantum phenomenon. So this is one reason that we do not teach these waves in school. Okay. Now, QCD has an interesting property. It is called asymptotic freedom. And as Misha pointed out, we do not see a similar effect, for example, in most of the studies in differential equations or PDEs or many other nonlinear problems. This tells us that the coupling constant in the theory, which tells us how gluons interact with each other or quarks interact with gluons, etc., is something scale dependent. As you go to higher energies, this coupling becomes smaller and smaller. And for a lower energy effect, the coupling grows large. This phenomena is called asymptotic freedom. Okay, so your coupling is dependent on scale. So at weak coupling, perturbation theory is in general successful in quantum field theories. However, for strong coupling, there is no first principle analytical approach yet. Okay. So you can ask, what sets the scale in Yang-Mills theory? Every quantum field theory is defined with a cutoff. For example, I like to mention lattice spacing, but any other cutoff would do fine. So this can be at a arbitrarily high energy level. And the scale at which the coupling becomes very strong is called the strong scale. And it is given by something called dimensional transmutation. So here is the formula. Lambda is the strong scale of QCD, which governs the spectrum of particles in the theory. It's Hilbert space, physical Hilbert space. And you immediately see that, and here G square is the coupling, which is scale dependent. And there is a beta naught, which is the first order renormalization group beta function, which is 11/3 n for Yang-Mills. Now you immediately notice that the appearance of G square is through exponential of -1/G square. Okay, hence this represents an essential singularity at G square equals 0. So we call this term, we call this as a non-perturbative as it does not admit a perturbative expansion in G square. So the mass cap in the theory is dictated by strong scale. Okay? Now, this is one perspective. It is essentially telling you that the strong coupling phenomena, for example, is responsible for all mass of the visible matter in the universe, all of us. Now, let me tell you a slightly broader perspective in quantum field theory. And I will start borrowing something from a talk that Mike Douglas gave in StringMath in 2011. So the motivation is following. Motivation is, can we make sense out of quantum field theory? Or when is there a continuum definition of quantum field theory? Both of these things are fairly difficult problems. So in Mike Douglas's comment, he says that, you know, most of the path integral formulation starts with the Euclidean functional integral. There is no essential difficulty in rigorously defining functional integrals, etc., and setting up perturbation theory. And he says a major difficulty that many mathematicians would consider QFT as still not rigorous is that standard perturbation theory only provides an asymptotic divergent expansion. And I wish this was the only problem, okay? We would do quite fine with it. But here is the thing. Actually, he gave this talk in 2011. And in 2012, there was this workshop, Mathematical Foundations of Quantum Field Theory, which was actually organized by formal people, Mike Douglas, Kevin Costello, and Arthur Jaffe. And the intention is, again, to find a non-perturbative construction of the quantum field theory, similar to part of the intentions of this program, but with almost completely different tools, okay? So Mike Douglas in 2011 invited me to talk about some work I did in my PhD thesis, construction of the supersymmetric gauge theories on the lattice. So in particular, n=4 super-Yang mills on the lattice, because this lattice formulation involves something called topological twisting, and Douglas thought that our construction can be used by mathematicians for proving certain things in n=4. However, at the time, I was very immensely under the spell of semi-classics and resurgence. I thought semi-classics could do fascinating things because of some ongoing work since 2007. And I also started to understand some things about resurgence. And I said, Douglas, that there is something more interesting that is keeping me awake at nighttime. And if it is okay with him, I would like to talk about it. And so at the end, my advisor, David Kaplan, ended up talking about lattice supersymmetry, and I was demoted to a shorter talk on semi-classics on R3x S1 with a very bare mention of resurgence at the end, essentially stating my optimism about the subject. But the good thing is, Gerald came to that meeting because I was coming, and because if he come, we could chat. And this was actually beginning of our collaboration, the fact that he came to that meeting. And during that meeting, I think we skipped some talks, and we pulled out of our bags these papers that we thought nobody knew in the high energy physics community in United States. This is the quite famous now work by, writing by Barry and Chris Hals, Infinity Interpreted. It's about divergent series, asymptotic series. And in that write-up, there is a section called Resurgence and Hyperasymptotics, which was very nicely written. And actually, there are many insightful comments throughout this write-up. And at the end, they say that this theory of resurgence is of crucial importance. Why? Let me tell you why I cared about this. Because from 2007 to 2012, I was able to calculate many things semi-classically. And this involved things which is second order in semi-classics, third order in semi-classics, fifth order in semi-classics. You know, genuinely fifth order saddle in the semi-classics, extremely suppressed, but for some physical observables, giving leading order effects, okay? And I thought that there was something deeper going on about the stuff that I was doing, and I was questioning myself. And Gerald was more interested in the quantum mechanical aspects of this idea, hyperasymptotics and resurgence, and I was interested in 4 dimensions. And we negotiated to make our ways to 2 dimensions. You know, we negotiated in 2 dimensions. And here is the book by Jean Eccal. Now, in the last 10, 15 years, some people are, in string theory, 15 years at least, in quantum field theory, 10 years, some people are attempting to answer this type of questions, whether or when a non-perturbative continuum definition of quantum field theory may exist, and we would like to reinvigorate this problem. And this involves a number of people that are, you know, quite well. Gerald is among them. Actually, Marinho started to use resurgence very heavily all the way to 2008 in matrix models. And there are, in 2011, there is important paper by Ricardo, Ines, and their friends, and later on, Gukov. You can hear from here and there are many talks by Kontsevich on the relation of resurgence and Picard-Lefschetz theory, which we also understood early on. And there are other works in math and topological quantum field theory by Costin, Garfalidis, and others. There is, of course, work by Witten on analytic continuation of path integrals and Picard-Lefschetz theory, but he never mentions the word resurgence. He mentions hyperasymptotics very appropriately, but never mentions resurgence. But the point is following. All of these physicists or physics-oriented mathematicians have something in common. There is a concept that all of them are very deeply influenced from. And this is, in some sense, relatively recent mathematical progress. And it is really based upon the work of Stokes, which unfortunately, you know, for almost a century did not attract enough attention. It's very deep work, in my opinion. And this recent idea in mathematics, the word is coined by important work by Jean Eccal. It's called resurgence theory. And a very close cousin of resurgence is hyperasymptotics, which is developed by Berry and House and building on earlier ideas of Dingle. Actually, Dingle, in my opinion, after Stokes, he made the first genuine contributions in mathematics to the divergent asymptotic series. He has a beautiful book I strongly recommend. And these ideas were known in some circles. Most importantly, Pham and his collaborators did very important work. And Boros, Zinjustan, and Bogomolny did quite remarkable things in quantum mechanics early on. But these things were not sufficiently appreciated, in my opinion. Now, I used to give this talk in 2012, and I kept this red item from there. The other things changed a little bit, maybe. In 2012, I used to say that resurgence theory changed or is changing the overall perspective on asymptotic analysis for both mathematicians and physicists alike. Okay. And I am actually extremely happy to see that, you know, this program is going on right now at Cambridge. You know, one thing I should add is actually there are earlier hints that a resurgent structure must underlie quantum field theory. This importantly involves operator product expansion that Misha, Arkady, and others developed. Okay. Now, this is the sort of big picture description that I would like to give, but let me now tell you what we are facing in quantum field theory. I can tell you about the two-dimensional sigma models or four-dimensional QCD or QCD-like theories. And both of them are asymptotically free theories. Okay, for sigma models, large N techniques works quite fine, but there are many unresolved problems at finite N. And of course, we all know that even after regularization and renormalization, perturbation theory is still a divergent asymptotic expansion. We can always ask the question if there is a meaning to perturbation theory. One thing which is very different between quantum field theory and more calculable systems is that in quantum field theory, up until fairly recently, there was no reliable semi-classical computational schemes. I will come back to this, okay? So the so-called dilute instanton gas is actually invalid. I put approximation in quotes because it is not approximation. It is really, in certain sense, it is nothing. So it assumes, starting that the inter-instanton separation is much larger than the instanton size itself, okay? But the instanton size in the theory is a moduli. It can be anything. It can grow arbitrarily large. So there is no meaning that separation is larger than the instanton size. Actually, in his famous lectures, Coleman called this infrared embarrassments, you know, the consequences of this. A resolution of this instanton size problem was suggested in a number of works by thinking these theories in a thermal box. But whenever you consider a thermal box and consider the regime of the theory where it becomes weakly coupled, there is almost always a phase transition, and you land on the deconfined phase where, you know, it is genuinely different phase of the matter. And so in particular, there is no semi-classical approximation, reliable semi-classical approximation for the confined phase, okay? There is also well-known results on incompatibility of the large N with the dilute instanton gas. This better be so because we trust large N calculations, but we do not trust the dilute instanton gas. And last but not the least, there is something called renormalon problem, renormalon ambiguity. This is a deeper and more technical problem. The date is wrong here. It should be 77, to Hooft's Erige lectures from 77, okay? And to my surprise, okay, all of these things are related, okay? And perhaps to most people's surprise. So here is the sort of philosophical perspective. So in order to say something new on an old problem, we must either have some new perspective or new tools or both, if we are lucky. And in one of his talks, Barry says, I like new things in old things. And I think I also belong to a similar philosophy, okay? I also like new things in old things. You know, if there wasn't a new thing in it, why would we care? You know, if there wasn't something deep and interesting in it, why would we care? And the new tools are both from mathematics and physics. As Misha pointed out, from physics side, we have this new notion of adiabatic continuity and reliable semi-classics. And from the mathematics side, we have resurgence theory and trans-series structure, as well as complex Morse theory, which is Picard-Lefschetz theory. Okay. Now, let me come to quantum mechanics, give an example in quantum mechanics and importance of critical points at infinity. This part of the talk, you know, it is already covered in many other talks, so I will be very brief about it so that I will go to the territory that I would like to talk about. So we can ask the following question, simpler than what 't Hooft asked. You know, can we make sense out of the semi-classical expansion of quantum field theory? And semi-classical expansion, I mean, there's a perturbative part, a calculable and reliable instanton terms and fluctuations around them. And we all know that all of the series entering here are asymptotic divergent series. And we are all familiar with the machinery of Borel resummation, which gives us some results. But if the Borel transform has a singularity on, for example, positive real axis, we say that there is an ambiguity in the sum. Okay. Now, what happens? So let's say in some quantum mechanical system, we did some perturbation theory. We can develop any order we wish by Bender-Wu technique. And we do Borel resummation. And at the end, we get a result of the following form. There is a real part of the perturbative result after Borel resummation. And depending on the choice of contour, whether we go clockwise or anti-clockwise around the singularity in the Borel plane, there is an ambiguous imaginary part. And this ambiguous imaginary part is universally, in quantum mechanical systems, it is universally a two-instanton effect, instanton, anti-instanton. We say that the perturbation theory is non-Borel summable, and as such, by itself, perturbation theory is sick. It doesn't mean that, being non-Borel summable doesn't mean anything bad. It means that there is a deeper structure there, okay? Now comes important work of Bogomolny and Justin. They consider double well potential, and instead of double well, you can consider periodic potential. So there is a dilute guess of instantons in quantum mechanics, and this is the textbook picture. There is instanton, anti-instanton, etc., etc. But actually, in reality, once in a while, there are two instantons very close to each other, and an instanton, anti-instanton fairly close to each other, satisfying such an hierarchy. Okay, so instanton size is much larger than the size of this correlated event. And the question that Bogomolny and Justin were asking to themselves was how to calculate the amplitude for these events, because they contribute to the physical observables. It is very similar to the cluster expansion in statistical physics. I think it is same. So they calculated instanton. When you have an instanton, its position is a moduli, but two of them, the relative position is quasi-moduli. And I will come back and make these statements very precise by talking about critical points at infinity, what kind of genuine saddles they correspond to, okay? But let me first describe what they did. So they calculated instanton, anti-instanton, but when it came to instanton, anti-instanton, actually the naive calculation is meaningless. Because instanton, anti-instanton is attractive, and hence there is some problem with the calculation. What Bogomolny suggests is that we can continue G squared to negative, do the calculation there, and come back to positive G squared, where the physical theory lives. And when you do this, depending on your way back to physical theory, you end up a twofold ambiguous result. This is interesting because from perturbation theory, we obtained a twofold ambiguous result. And from the non-perturbative sector, we are obtaining a twofold ambiguous result. In fact, these things, these twofold ambiguities, are not random. If you study large orders of perturbation theory in this periodic potential, there is an n factorial divergence. There is an n-1 factorial, n-2 factorial, so on and so forth. But you can go ahead and calculate, for example, instanton, anti-instanton contribution and to, real part and imaginary part of the energy. And the imaginary part has two instanton factor here, and it also has perturbative fluctuations around them. You immediately see that there is a conspiracy going on between fluctuations around the saddle, these prefactors, and the way that the series diverges, and n factorial divergence, n minus n factorial divergence, so on and so forth. So it turns out the following is true. And this is the notion of Borel-Ekal summability. The imaginary ambiguous part of perturbation theory, which is twofold ambiguous, cancels exactly with the imaginary ambiguous part of the instanton, anti-instanton correlated events. One of these is data from perturbation theory. The other one is data from non-perturbative sectors. And these two different discontinuities conspire in such a way to give a meaningful and continuous result across argument of h bar equals 0. Okay, so this is the Stokes phenomenon. And I must say that this kind of cancellation, we show actually, Bogomol and Zinustan showed only leading order here. Gerald and I showed these structures, subleading structure, but I must say that it is actually, after some time, I realized that it is actually implicit. They do not calculate numbers, but it is implicit in the work of Pham and his collaborators. Okay. Now, you can ask, why did this happen? And it takes us back to the problem of, Stokes phenomena and the rainbow. Actually, Stokes was trying to understand supernumerary rainbows. And this part of the talk I borrowed from the talk that Michael Berry gave, but the link is no longer available, unfortunately. I do not know why. But the situation is very similar. Also, this is ARA's original title, on the intensity of light in the neighborhood of a caustic. Okay, so there's a caustic, there's a dark side, and there's a bright side interference pattern. So, and the intensity pattern is actually square of the ARA function. And Stokes was trying to understand ARA's integral. This is like, for us, like PET integral, and it's a fairly difficult integral. And actually, he found the correct results, but he was puzzled about his correct result almost for 10 years. And I will tell you what. In fact, historically, ARA himself tried to calculate this integral, and he was able to find only the first two bright nodes on the bright sides by doing Taylor series expansion. But Stokes in this work developed counterparts of steepest descent method, the steepest descent method, and he calculated this integral both on the dark side as well as on the bright side. He found these oscillatory sum on the bright side and exponentially decaying evanescent wave on the dark side. Okay. Now, but here was his puzzle. It is very easy to phrase. First of all, he was very pleased with this result because it was really an important issue of the time concerning, wave theory of light and interference effects. But the puzzle was following. The puzzle is 1 is not equal to 2. What do I mean by this? How a continuous function, here, this ARA function, can be represented by 2 exponential on one side. This is the bright side, sum of 2 exponentials, and expressed by just 1 exponential on the others. In particular, continuation of this exponential decay to negative x produce only one of the exponential, and his puzzle was how did the second exponential emerged? And almost 10 years later, he solves this problem, and he realizes that these terms that he found were the first terms of a divergent asymptotic series. Since this is very well explained in earlier lectures, I will not explain how to go from here to this discontinuity of the constants multiplying these two exponentials. But I will just give a geometrical picture. Okay. This is ARA's integral. Of course, Stokes did not have Mathematica, and we have Mathematica. We can easily plot this. And on these dark sides, only one the integration tells us that start here and end up here. It start in this domain and end up in this domain. And you can do this by passing through the saddle I call 0. Okay. But now, as the argument of the coupling approaches 2 pi over 3, something interesting happens. This steepest descent path passing through this node here, 0, approaches to the other one arbitrarily closely. And exactly at the Stokes line, to go from here to there, you pass through both of these saddles. And just after the Stokes line, there is no direct path from here to there. You have to take a connection, like a connecting flight. You have to go from here to there and come back from there to here. Now, at this stage, actually, instead of one saddle contributing, 2 saddles started to contribute. Mathematically, we call these things Lefschetz thimbles. And the limit of the Lefschetz thimbles at argument of x being 2 pi over 3 from the negative sides is equal to sum of these 2 Lefschetz thimbles from the positive side, as it is clear from these pictures. And the connection of these to the divergent asymptotic series is that this integration over thimble is actually this choice of integration over thimble. You go from here to there or from here to there. This is actually left-right Borel resummation that we deal all the time. So this there is a very precise correspondence between Lefschetz thimble integration and Borel resummation. Okay. This is what he realized, okay? And the effect that is taking place in quantum mechanics is essentially very similar. But now, actually, as a new ingredient to my earlier talks, I want to describe these things that Bogomolny and Zinustan found more rigorously. And I think both of them understood these things very deeply, and I have a suspicion that maybe they may even know it, but it is not written up. So I want to talk about this concept of critical point at infinity. And first of all, in a high energy physics community, there is a very bare, actually in any community, there is a very bare mention of critical point at infinity. If you go to Coleman's lecture, Aspects of Symmetry, it was suggested that, you first, you can do the following first. You can compactify time direction to a Euclidean circle. Then the interaction between an instanton and anti-instanton, or instanton and an instanton, is modified as follows. There is this, exponential minus tau term, distance from one side. Since you are on a circle, there is also distance from the other side, and the interaction between an instanton and anti-instanton is given as such. And if you look to this section, critical point is at beta over 2. And if you take beta to infinity, then critical point moves to infinity. This is the concept of critical point at infinity. Now, Coleman talks about this, and it was suggested that the true critical points in the instanton analysis, by this I really mean a reliable instanton analysis, needs to be found at infinity. However, unlike many advisors of this wise man, this one is not taken by heart by physics community. I think nobody cared. In 2014, I wrote a paper explaining some connection between Lefschetz thimble and resurgence with Daniele and Alexei Cherman. And after that paper, we received a message from Witten asking us if our bion configurations were critical points at infinities. And at that moment, I remembered this word, critical points at infinity, from Coleman's, and I decided to go back and look there and what they say. But Witten gave us one other path, actually. He told us that there is infinite dimension. There is a discussion of this in Pham's paper on homology decomposition of the Lefschetz thimbles. Okay, and we decided to go there too. And indeed, it turns out that most of these bions are actually configurations on the thimbles of critical points at infinities. And this is actually written very explicitly in these two papers, almost simultaneous and completely independent, by Nikita Nekrasov and our group. And here is the thing. Let me make the example even nicer so that you appreciate the critical point at infinity much better. You know, instead of ordinary quantum mechanics, insert some fermions. Just, you can set fermion number to 0, it will drop you back to quantum mechanics. It doesn't matter. You can integrate out fermions and they will give you this kind of Lagrangians where potential is modified by a quantum term. So this is, the potential is tilted by a term of order of h bar, okay? Now the interaction between an instanton and instanton becomes like this, and there is an extra term, quantum term, and instanton and anti-instanton are like this, and there is a quantum term, okay? I would like to calculate these amplitudes. Now, here is the very interesting thing, okay, which distinguishes critical point at infinity from the regular Gaussian critical points. Go to this instanton, for example, critical point. There is a critical point is at beta over 2. It goes to infinity as beta goes to infinity. And you can calculate the contribution, you know, the integrand at this critical point. And it gives you 0. So the critical point, as well as its neighborhood, does not contribute. And in this case, the steepest descent cycle is R. So you need to do an integral over the positive, over the real axis. But now look at this. If you are considering instanton, anti-instanton, for which the interaction is attractive, the critical point at infinity is still same. It is at beta over 2. But now steepest descent path is not on the positive real axis. It is perpendicular to that. It moves to the complex domain. And you go with this shape into the complex domain, and this is your Lefschetz thimble for this integration. You do this integral actually by taking, depending on your argument of G, it is either plus exponential of plus or minus I pi zeta, and zeta was my deformation of the potential, okay? Now, here from the instanton, anti-instanton, because of the choice of the thimble, you get a twofold ambiguous result, except when zeta is integer, and it is a very nice meaning, that is supersymmetric case. But generically, you get twofold ambiguous results. And so let me summarize this critical point at infinity. Unlike Gaussian critical points, the critical point at infinity by itself does not contribute. However, its thimble gives the major contribution. So in this thimble, for example, for instanton, anti-instanton, the major contribution, let me do instanton first. You know, the thimble is R. Major contribution comes from a scale, log A over G, where G is the coupling. And in fact, I can go ahead and solve these equations of motion, but this is not usual Newton's equation. It's a holomorphic version of the Newton's equation. And this is not just the classical potential. It is this quantum modified potential. And this bion is actually turns out to be dominant configuration on that thimble, okay? And here's the interesting surprise. If you do this, solve this equation for the other solution in the game, for the I bar configuration, you know, you find a solution which has both real parts and imaginary parts. They look discontinuous. They look, if you look at the face of them, they look almost meaningless, but their action is finite. Their action is 2 times instanton action. And this is the configuration which dominates the path integral. Okay? Why these configurations are super important? First of all, despite the fact that they live in the complex domain, you have to take them into account for sure. For example, zeta equal 1 case here is the supersymmetric case. In this, for periodic potential, it is known that supersymmetry is unbroken. So there must be a cancellation between contribution of this saddle and that saddle. And it turns out that the contribution of this real bion to the ground state energy is negative. Actually, if you didn't account for this complex solution, which lives on this critical point at infinity, on the thimble of this critical point at infinity, you are in huge trouble because it would give you, it would violate supersymmetry algebra, which is impossible, which tells you that you have to include these complex and even discontinuous looking solution. Okay. Now, this is the story in quantum mechanics. It tells us that the critical points at infinity are extremely important. Taking them into account properly is extremely important. That's important for the consistency of the way that we are treating our path integral. Now I move to quantum field theory. In quantum mechanics, we have seen first instances of this Borel-Ekal resummation. And actually, exact WKB method shows that this kind of exact cancellation between perturbative and non-perturbative effect continue to all orders. This is the context of the DDP formula and exact WKB. You can ask whether such a nice cancellation can take place in quantum field theory. Okay, here is rough story. Okay, so we can work on Yang-Mills theory on R4 or bosonic CPN on R2. And many people told us that this kind of cancellation between just instant-on effects and the Borel ambiguity of the perturbation theory is impossible. That's correct. But there is another thing at work. Okay, so let me first say why it doesn't work on, for example, CPN on R2, but it doesn't really matter. If you calculate instant-on, anti-instant-on contribution, maybe Yang-Mills is also okay. Calculated in some way, it gives you an ambiguity here at 2s instant-on position. This is very far from the origin of moduli space, but in the context of Yang-Mills, 't Hooft realized that the Borel transforms has other far more important singularities much closer to the origin of the Borel plane. These are called ARA renormalons. And these are not due to factorial growth of the number of diagrams, but they come from phase space integration and from a fixed set of diagrams. So the perturbation theory is very wild. Okay? So 't Hooft called these things, these singularities, ARA renormalon, hoping that maybe there is something to be found. Okay, but no such configurations were known for a very long time. Okay, this is a real problem in QCD or Yang-Mills theory because it tells you that perturbation theory as it stands is ill-defined. And the question is, how can you fix this by starting with microscopic dynamics, by a genuine saddle point analysis? To answer this question, you have to first come up with some historical point of view. Historically, it is believed to be the following. This is something Parisi mentions in 78. If the theory is renormalizable, Borel transform has new singularities which cannot be controlled by semi-classical methods. These are the renormalons, okay? And he refers to 5 to 8. 5 is 't Hooft, can we make sense out of QCD? And 't Hooft says, actually says that these are not semi-classical. Even in 2015, he has a writing which says the same thing. And it is likely that these singularities are related to quark confinement and mass gap, okay? But this is not some, 40-something years old myth, etc., etc. one of the most brilliant guy of my generation is Marcos Marinho. And he, in 2012, he wrote the following in his 2012 review. In realistic quantum field theories, perturbation theory is so wild that it is not feasible to pursue the program. This is the resurgence program, but maybe only in some special theories like Chern-Simons or N=4, where some partial results exist. And he says the idea of resurgence have scarcely been used in quantum field theory. However, as Misha sketched at the very beginning, I actually, in 2007, I started to ask a new question. My question was following. What happens if we can make the most interesting quantum field theories semi-classically calculable? By this, I really mean Yang-Mills theory, CPN, supersymmetric Yang-Mills, QCD, etc., etc. And the question was, is this even possible? And when I asked this even after writing the paper, many people thought that this was a very obviously impossible thing, especially in non-supersymmetric quantum field theories in thermodynamic limits. You cannot have a reliable semi-classical calculation in thermodynamic limit. But in 2007, this perspective started to change. I was able to convince some brilliant people. This included Misha, Yafe, Popitz, Argyres, Dune, many friends of her. But, our larger community in quantum field theory responded to this idea by essentially ignoring it. I like to make this joke, but it's a joke about myself. But the joke is that, Meissner effect is a very well-known phenomenon in superconductivity. I want to say that both QCD as well as SUSY QCD exhibited Meissner effects. And these were for orthogonal reasons to the set of ideas that I was coming up with my collaborators. I hope this doesn't offend anyone. Now, here is the idea of adiabatic continuity, okay? So if you consider a field theory on R to the D, this is one incarnation of it, and then the incarnation that I like the most. Usually what people do is they compactify a circle, and this is interpreted canonically as a thermal circle. And this corresponds to, when there's a circle, there's a trace. When there's a trace, you are calculating partition function. This corresponds to calculating partition function at finite temperature. But we want continuity. But this is almost impossible to achieve because at the face of it, because if you look to beta goes to infinity limit, only ground state contributes. Beta goes to zero limit, everything contributes. It is quite inevitable that there will not be a singularity on the way in between. And I do not think that there's a counterexample to this. If you do not do some games, by softly breaking some order parameters and stuff like that. So there is always a phase transition. But what I wanted was this notion of adiabatic continuity. Then I could have a weakly coupled domain, continuously connected to the strongly coupled domain, and I could do analytic calculation. So new idea from physics is following. And I am sorry from mathematicians. This is not present in any quantum field theory textbook. I know that it is not very canonical point of view, and we should write something about it as a textbook, I suspect, okay? Because this is the part that I receive most, not objections, but discomfort. But there are some interesting mathematical works starting now. But new idea from physics was following. Prevent phase transition by using circle compactifications with either judicious choice of matter or boundary conditions, okay? And in fact, this was not undone. This was already there in the supersymmetric theories. Witten in 1980 calculated Witten index not using partition function, but a graded version of the partition function, -1 to the f. But because of the symmetry, supersymmetry of the theory, there was an exact cancellation, and this problem I mentioned here did not exist. you could go to all the way to small circle and still only 2 states contributed and all the rest canceled. And in 2007 and 8, I used this quantity in some non-QCD, non-supersymmetric theories, and then generalized them with Leryov and Misha Schiffman to many other QCD-like theories. And this idea has its origins, again, not in continuum field theory, but something called large N reduction or large N volume independence from lattice gauge theory. And that was the origin of my intuition, more so than, actually both supersymmetry as well as this large N volume independence. Now, what is unusual for a mathematician about this setup, okay? The unusual thing is following. Let's say we are dealing with CPM fields. The boundary condition that Gerald and I put in our paper is something like this. You have an N field, which is a capital N component vector, a complex vector. And we impose this boundary condition by using the flavor symmetry of the theory, omega F. And what happens when you do that? This is very interesting, actually. The interpretation of this omega F, both from path integral, Hilbert space, anomaly perspective, is very interesting. We wrote this by some intuition from lattice gauge theory. Let me first tell you that intuition, because my time is wearing up. If you do regular compactification, okay, you get spectrum in units of 2 pi over L. Okay, this is the Kaluza-Klein decomposition, very standard. If you do R compactification, the spectrum is in units of 2 pi over Ln. Here comes the catch. Even if you are at finite L, even if it is arbitrarily small, if you take n equal to infinity, the perturbative spectrum is continuous. This is as if in the n goes to infinity limit, even your theory is at arbitrarily small S1, it emulates the theory on R2. This was our intuition for the boundary condition. Okay, and this notion is called large N volume independence. But in this talk, I will work with this setup at finite N and benefit from adiabatic continuity. Here is the thing. Here is the thing. It turns out that I will not describe this in detail. I will tell you what is happening. It turns out that this CPN model, CPN-1 model on R2 has a mixed anomaly between its global symmetry, which is PSUN, SUN mod ZN, and charge conjugation symmetry. This is pointed out in Komargotsky et al. And it turns out that there is a unique way to preserve this anomaly upon compactification. Okay, so let me go here. There is an anomaly here. And if you do regular compactification with no twist, you do not preserve this anomaly. It betrays the, it betrays the nature of the theory. If you want to preserve that anomaly, it turns out that you must use the boundary condition that Gerald and I proposed in 2012. This is another means, but it also tells us the following. If we obtain our results with, trustable methods, it doesn't matter if it comes from lattice gauge theory or, mathematics or supersymmetry. If we obtain our results with sound methods, they must agree with each other. If they do not, that's a great thing. That means one of them is not right. But this anomaly consideration told us that if you want to preserve a mixed anomaly of the theory on R2, you must use this boundary condition that Gerald and I used. Here comes the very interesting thing to my mind, and I understood this thing many years later in 2018 with Gerald and Yuya. If you do this twist in purely bosonic theory, it actually kills the whole Hilbert space, leaving only ground states. This is as if you are calculating something like a Witten index in a non-supersymmetric theory. To my mind, this is fascinating. This is the Hilbert space reincarnation of this idea. Okay, what happens? If you look to topological configurations, for example, instantons, with or without twists, I borrow this title from you too, okay? What happens is that if you insert this twist, the usual, if you do not insert this twist, if you look to instanton as the moduli size changes, nothing happens. An instanton is an instanton. But if you put this twist, an instanton splits up to 3 constituents. Each one of these things, this is for CP2, I think, and in general, n constituents. Each one of these things have action as instanton divided by n, okay? So these are the tunneling events. This is more mathematical page. Their action is BPSD instanton action divided by n. And you can show that these fractional objects combine together to give you BPSD instanton. And the sum here gives you, ironically, beta function, okay? And this is not just an accident for CPN model. It's really something taking place exactly in the gauge theory. But here comes one of the heroes of my story. If you go ahead and calculate the amplitude of these fractional instanton, anti-instanton events, as Bogomolny-Zinjustan did, or more modern perspective, as a critical point at infinity and finding its thimble and doing the integration, for k bar, this is fractional instanton again, you found a nice real part and you find an ambiguous imaginary part. From an old school point of view, this is disaster. It tells you that semiclassics at second order is void of meaning. But from the modern point of view, this is the best thing that we can ever get. Because this CPN model, you can compactify it on a circle, as I said. And in Born-Oppenheimer approximation, you can reduce this theory to, if you apply Born-Oppenheimer twice, and this theory admits that, you reduce this theory to a particle on a circle with n minimum on the circle. And it's very easy to study the perturbation theory at large orders. There is a now very nice Mathematica program written by in Süleyman Pasic, which does arbitrarily large orders, 500 if you wish. And of course, perturbation theory is asymptotic and divergent. And you sum up you do Borel resummation and you get a twofold ambiguous result. And remarkably, of course, expectedly by BZJ, the twofold ambiguous part of the perturbation theory, as you cross Stokes line, this ambiguity cancels with the twofold ambiguous part of fractional instanton, anti-instanton. Okay? But at this stage, exactly at this stage, you can say, oh, this is nice. A magic happens. The magic is following. These ambiguities that cancel are of the order of 2s instanton divided by n. This is exactly the IR renormalon territory of 't Hooft and François David also found in this model. So our claim is that this was our challenge at the time, that renormalons can have a semi-classical origin if you push the theory to a semi-classical domain. So these neutral bions and other neutral topological molecules are semi-classical realizations of 't Hooft elusive renormalons. And I think, you know, as an answer to this question that 't Hooft asked, can we make sense out of QFT? I think we have a chance because we understand two sources of origin of these ambiguities and we know how to cancel them. Now, this was more or less the talk I have given in 2012 at KITP. And at the end of the talk, I gave a talk about QCD adjoint, but exactly the same sketch. At the end of the talk, David Gross, another person that I admire and respect a lot, asked me the following question. Tell me, except for 't Hooft, who would care about what you did? First of all, I was actually flattered by the question because he thought 't Hooft would care. Okay? And to me, 't Hooft is one of the deepest thinkers of this field. And I said, you know, me being me and a bit younger, I care. And I have 3 friends who care. 3 friends being probably Argyres, Gerald, and Misha, okay? But in principle, we as a quantum field theory community should all care. I think Gross started to care. In 2014, he gave these lectures, Millennium Prize Problem, Yang-Mills theory. And he says, you know, let me revert. One way that has not been used for constructing quantum field theory, Yang-Mills theory, which might in the end turn out to be proof of both existence and its properties, is to make mathematical sense out of these divergent expansions. Okay? Much like you can make sense out of other asymptotic series and mathematical objects if you can control various singularities. That's important, the word control. The singularities you get when you construct Borel transform. There is in fact a revived interest in making physical sense out of such expansion. That might be actually a way of, a different way than people typically use to define the theory and prove its existence. Well, this is great, coming from him. Now, many people make the following objection. I said that here, the singularities of the baryon, by the way, that's my last page. The singularity associated with baryon matched exactly with the ARA normal on location in the CPN. I often said that in my talks, that was a numerical accident. The best you are entitled to expect is that in semi-classics, you will get a singularity at order 1 over n, and from standard trinormal analysis, you will get a singularity at order 1 over n again. But there is no reason for the coefficient to agree. And in fact, if you go ahead and look to pure Yang-Mills theory, coefficient of leading, the position of the leading ARA normal on singularity is 6 over 11 times 1 over n times instanton, anti-instanton position. Okay? But the semi-classical analysis give you 1/2. There is roughly a factor of 2 difference. And I always said that this is not an inconsistency, okay? Because this is a difference in pure numbers in the locations. And there is a good reason for this, because you do this in a semi-classical domain where weak coupling analysis is reliable. You do this, you do get this in the strong coupling domain, where the theory necessarily runs to strong coupling. It is very natural to my mind that there can be a Borel flow between these two. This is a point not crystallized yet, but I hope to make some progress about it very soon. But my suspicion is that, for example, sometimes it is said that gluon condensate and neutral baryon may be different things. They are not. Actually, neutral baryons are the origins of the ambiguity in gluon condensate. I think this is something that more phenomenological QCD friends need to digest in time, and we need to learn from them many things. But the gluon condensate, if you calculate on R3 process 1, has a theta dependent part, which is unrelated to perturbation theory. But there is also part coming from these neutral baryons, critical points at infinities, which is twofold ambiguous. But this analysis is reliable when lambda Ln is less than 1. Actually, if you extrapolate this analysis to the boundary of effective field theory, it will give you lambda to 4, the usual ARA normal on location. Okay. And there are some reasons that one should do that. Now, my conclusion and prospects, okay? It seems plausible that resurgence, Lefschetz thimble decomposition, and various other things can be used in combination to provide a definition of path integrals. And perhaps in some cases, non-perturbative continuum definition of hopefully asymptotically free theories. At least in quantum mechanical examples like particle on a circle or double well potential, exact WKB method is actually the statement that this Lefschetz thimble decomposition is actually exact. I think part of this statement, at least in my opinion, in quantum mechanics is shown by using these exact WKB methods. You have to just translate it to het integral, and this is something that is being pursued nowadays. I hope that this construction may have practical utility and region of overlap with lattice field theory. And one can check the predictions of this formalism. At this stage, I must say that the idea of adiabatic continuity now has been investigated by lattice field theorists for almost more than 10 years, but the most impressive result appeared this year by Massimo Delia and his friends from Pisa, and it works essentially, okay? It works much better than you expected. There's a numerical proof for that. Now, resurgence idea provides a more refined classification of non-perturbative saddles with respect to topological classification. This is something that Gerald and I call resurgence triangle. In particular, non-self-dual saddles and non-BPS saddles, and these critical points at infinities are meaningful, and they should be carefully incorporated. Let me stop now, sorry.
Okay, let's thank the speaker. And questions, please. Questions, comments, general discussion.
Yes,
so
please.
I have a comment relating your ideas to the sometimes neglected part of the standard model in 4 dimensions with no compactification, then we find to the 4th theory. And Eric Panzer and John Gracie and I have been having discussions with David Wallace and Alan McCain, who along with Lepatov and Zinjustan and Brezan have predictions for the large order growth of the beta function. It becomes a matter of interest because this beta function has now been calculated to 7 loops, and Eric Panzer has reliable method for estimating it at the 1% accuracy level up to 12 loops, or at least the scheme independent parts. So the long-standing historical question which you've addressed down here is whether the classical solution, let's call it the instantile of Lepatov et al., is swamped by renormalons, is modified by renormalons, or dominates over renormalons. And
it's a very interesting question.
And Latouft has an argument about this. Everyone relies on Latouft's wisdom, you know, deep down there when we don't know what to do, we look for what wise and original people said. And Latouft's argument's rather simple to state, is that the renormalon doesn't modify the Lepatov prediction because it exists, it doesn't exist in any dimension less than 4. And if we do the calculation right, sum all orders before letting epsilon go to 0, not the wrong way, which is letting epsilon go to 0, then we won't see it. So Alan McCain is giving a talk in John Grace's group about this in Liverpool at present. We're trying to refine our calculations, and we're able to visit that question. Now, one final comment. When I say the Lepatov prediction, there were 4 papers in that. One was by Lepatov, one was by Zinjustan and Brezan, and they agreed. Another was by Wallace and McCain, who agreed with those first 2 papers. And the 4th was by Wallace and McCain, who disagreed with themselves in the previous papers. In particular, there's no contribution from the Bessel function in Lepatov's paper, only the Bessel function at 0. So that the data that we have, tentatively estimating 12-loop contributions to the beta function, favors the 4th of those papers and not the original Lepatov one. So these ideas that you've touched on are actually surfacing in that practical world where we don't know 500 orders of perturbation theory.
Exactly, yeah.
But in only this particular case, it used to be 7 or 8 and now 12. Thank you for letting me make that remark, because I think it directly relates to things you've talked about.
Actually, I can make a remark about your remark. The argument of Lepatov is used by, I think, Bogomolny and Fatev, saying that there is a singularity at location 2 times instanton action, instanton to SI. And this is very commonly accepted in the literature, that this is the leading non-BPS configuration that can appear as an ambiguity in the Borel plane. But I want to challenge that, okay? The idea is following. If you consider in many gauge theories, even in sigma models, if you consider instead of SUN theory, SUN mod ZN theory, which is PSUN theory, you change nothing locally, okay? So it is similar to a curious case of the dog, in the Sherlock Holmes story, Silver Blaze. The dog does nothing. So the theory, as you go from SUN to PSUN, locally nothing changes. Okay? But the interesting thing is, locally, the bundle topologies, the bundle topologies in PSUN are much, much finer. There are actually configurations which has topological charge 1 over n and action 1 over n compared to instanton. But here is my point. This configuration does not belong to SUN bundle. But if you take this S instanton divided by n, even on R4, okay, or infinite volume, with then some instanton, anti-instanton in the PSUN bundle, that configuration can be uplifted without obstruction to the SUN. So I do not think that, the canonical wisdom in this subject is actually correct. So this is something I am thinking about right now, but it is really a different talk of its own. So in particular, I do think that this Bogomolny-Fateev argument basing on Lipatov, I think that it is flawed.
Well, I just make the comment, we are testing it with the best data that we can. Imagine the labor that has gone to finding the exact 7-loop beta function in the MS bar scheme and estimating its scheme-dependent part up to 12
I actually secretly follow that.
Yeah, well, I think it should be talked about publicly. So maybe you'd add a little comment about this work done by Oliver Schnetz and Eric Panzer and the link to your next talk, because I've been following it with great interest and with admiration.
Thanks.
Any more questions or suggestions, maybe comments? Okay, then I think we have to thank the speaker again for a very nice and, I would say, encouraging presentation, inspiring and encouraging presentation, and we will close this session with that. Thank you.
Thank you very much.